And welcome back. This was the problem you were going to graph on your Canvas notes, y equals 0.25x. Let's go ahead and do it together. We are going to plug in the points -2, -1, 0, 1, 2, and we're going to find those y values and then plot them. So this is y equals 0.25 to the -2. Again, 0.25 is 1/4 to the -2. Negative means I flip it, so this is going to be 4 squared, and that's 16. So y equals 16. Pretty big. Then we got y equals 0.25 to the -1, and again, up here, that means the negative flips it, so that's just 1/4 to the 1, which is 4. So that's 4. And then we have y equals 0.25 to the 0 power. And anything to the 0th power is always equal to 1. So that's 1. And so on. 0.25 to the 1 is 0.25, or 1/4. I'm going to write it as a fraction. And finally, squared, we end up with 0.25 squared. Decimal wise, I'm going to need a calculator to do that. But if I change this to a fraction, 1/4 squared, I know that that's 1 squared over 4 squared, which is 1/16. And hopefully that shouldn't be too huge of a surprise with everything we've done with negative exponents so far, knowing that it's 16, 4, 1, 1/4, 1/16, right? Kind of does that pattern when there's no other number. We have our 5 points. We are going to need to go up fairly far on this one because we got to get as high as 16. So let's go by 2s. Let's go by 2s. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so let's label it to make sure people know that we're going by 2s. All right, let's change the color and plot our points. Let's go with a nice pretty red this time. All right, -2, 16, we're way up here. Yep. -1, 4, we're down there. Notice how quickly we dropped going in between 1. Like, that's a large drop that we just had. 0, 1 is right there. 1, 1/4 is really close. I don't even know if I'm going to be able to get that close. And then 1, 1/16, or 2, 1/16 is even closer. It's so close to the line that I probably can't even tell the difference between them. And my pen gets mad at me for even trying. So there's my 5 points, and we connect this curve. Notice how steep it is, and then it levels off very suddenly. And again, it approaches the x-axis, but it doesn't cross. So there we go. Again, if you're having problems, make sure you're asking questions before you're moving on, but let's go down to our last set of examples. We're going to do an exponential decay word problem. Now, we're going to use the same formula that we did in the last section, which was y equals a times 1 plus r. But this time, because it's decay, we're going to subtract r. In growth problems, we did y equals a times 1 plus r, right, times t. This right here is because of the growth. When we're growing, we're adding the percent. For decay, we are going to subtract it, right? The subtraction is going to make decay. So let's go ahead and do this example together here. The number of acres of ponderosa pine forests decreased in the western United States from 1963 to 2002 by 5% annually, right? Notice percent decrease. Again, to point it out, percent decrease is what tells us that this is exponential. Okay, in 1963, there were about 41 million acres of ponderosa pine forests. Part A, write a function that models the number of acres of ponderosa pine forests in the western United States over time. So it's not giving us a specific amount of time, it's just telling us write the function, which means we need to take our formula and plug in all the appropriate numbers. So A is my starting value. This is just like the last section. B is my percent change, my growth, or in this case, decay. And T is time. So, my starting value. How many ponderosa pines did I begin with? In 1963, there were 41 million. Now, I'm not going to write 41 as a million. I'm just going to write 41, and we'll do everything in terms of millions. Okay? All right, so that's 1 minus, what is my percent growth, or my percent change? 0.5% annually. Now, remember, just like last time, we need to change our percent to a decimal. So instead of this being 0.5%, this is going to be 0.005 as a decimal, because we're going to move the decimal over twice, right? So that's 0.005, and we're not given time, so that's t. So we'll simplify this. 41, 1 minus 0.005 is 0.995 to the t. Let's erase that scribble. So there it is. That is my, let's just redo that whole thing. Right? It looked ugly that way. Yep. So 4 times what we say, 0.995 to the t. So that is the model that represents this. Again, I got it because the starting value was 41. The percent growth was 0.5%, which I changed to a decimal. And then I'm not given a time, so I'm just t. Okay. Part B says, to the nearest tenth, about how many millions of acres of ponderosa pine forests were there in 2002? So let's use this model that we just came up with. Y equals, we started with 41. We're decreasing by 0.995. But how much time has gone by? So from 1963 to 2002, how many years went by? Okay, 70 to 2000, that's 30. And then we've got 2 plus 7. So 9, I'm guessing 39 years is what we're looking at here, right? 7 to get up to 70, then 30 to 2000 plus 2, 39. So this is to the 39th power. And just like last time, it does not make sense to do these problems without a calculator. So let's use a calculator to do it. 0.995 to the 39th power just ain't happening on paper or in your head. So 0.995, and remember we're using that x to the y button. That button to the 39th power is 0.822. And then I'm going to multiply that by 41. And I get 33.7. What did they say to the nearest tenth? 33.7. So 33.7. There were 33.7 million acres of ponderosa pine. And that's all we've got today for this lesson. You can head back to your Canvas, find your daily assignment on there. Thank you for watching, and hope you have a great day. Bye.